Hey, it's Neil Smith here. Hope you're doing well. The following problem seems a bit overwhelming, but be patient with yourself. It's just adding, subtracting, looking some numbers up in tables, throw in a few nuances, a couple concepts to keep straight, and before you know it, you'll be doing these problems. They're not that bad. You got this. All right. Problem 5. Determination of compass error by azimuth of the sun. Here we go. Problem 5. And we need our givens. Here's the given. And what they give us in this problem is they give us the date, February 21. The date is equal to Feb 21, and that is 1981. And then they give us the zone time, which is 8:23. Zone time equal 8:23. And they give us the DR position. DR position, which is equal to latitude 21 degrees, 44.0 minutes south, and longitude 80 degrees, 14.0 minutes east. And they give us the sun's bearing, 96 PSC. Sun bearing equal to 096 degrees PSC. And they give us the chron time. They give us the chron time, which equals 3 hours, 25 minutes, 3 hours, 25 minutes, and 19 seconds. They'll give us the chron error, which equals, chron error is 1 minute, 52 seconds. So 1 minute, 52 seconds, and it's fast. If it's fast, we subtract it. And now they'll give us a variation, which equals to 5 degrees west. And they'll ask for a deviation. See, in the end of the problem, they say, what is the deviation of the standard magnetic compass? So first thing we need to do is find the approximate GMT, make sure we're in the right date and everything. So find the approximate GMT by taking the zone time, which is equal to 8:23, 08:23. And then we can take the longitude, which is 80 degrees east, and divide it by 15 to get how many hours away from Greenwich Mean Time we are. So 80 divided by 15 equals 5.3. 5.3. So we just need the full number, 5. It's less than 0.5, so we round down. So we get 5 hours. And do we add it or subtract it? Let's draw a little diagram here to figure that out. So if this is the prime meridian, 0, which is Greenwich Mean Time, we draw a couple time zones, and we say if we go east, we add east. If we go west, we're subtracting west. If you think like New York to California, you subtract. But California to New York, you would add. So now our longitude is east. So to get from the east back to the prime meridian or Greenwich Mean Time, we're going to minus. So we're subtracting 5 hours. So we say subtract 5 hours. 3, 2, 8 minus 5 is 3. So it looks like we are sitting here on February 21st at 3:23. Same day. So let's look at our cron time and get the actual GMT. So we take our cron time, which is equal to 3:25:19, 03:25:19, and these are hours, minutes, seconds. And then we get our cron error, which is equal to 1 minute 52 seconds. 1 minute 52 seconds. Do we add or subtract it? It's fast. We subtract it. Okay. So you can't take 52 from 19, right? We're going to borrow from this minutes column. So this is going to end up 24. And this, we add 60 to it. So it's going to end up 79. Now we can do it. 79 minus 52 equals 27 seconds. 27 seconds. 24 minus 1, 23 minutes. 3 hours. There we are. So we're looking good. 3 hours, 23 minutes, 27. That's what we got from our zone time calculation. Approximate GMT, they're close. There's a possibility that this could be 12 hours different. So it's not. So this is GMT equals 3 hours, 23 minutes, 27 seconds on February 21st. The date is important. This is all 1981. Okay, so here is our GMT. Now we can get the GHA, or Greenwich Hour Angle. So GHA, and we'll get that first for 3 hours. So 03 hours. And then we'll go into the increments table and get the GHA for these 23 minutes and 27 seconds. So we'll get those values. And then the declination values are going to be right there. So we're going to get the declination, and then we're going to get the D correction as well. Good. So we'll set that up. Now we'll go into the Nautical Almanac, and we'll find these things. So we're looking February 21st. So it's going to be near the beginning, July, April, March, February 27th, February 21st, right? So Feb 21, sun, 3 hours. Here's again the day, and we're looking for 3 hours. Look at that. Good. So we'll just triple check. Feb 21. Boom. 21. 3 hours. Good. So we're looking at GHA, degrees and minutes, 221, 34.5. 221, 34.5. 221, 34.5. 221, 34.5 degrees minutes. And the declination is going to be right there as well. 221,345. Declination. See the south? You bring that down. It's kind of implied. South 10, 37.2. South 10, 37.2. So south 10, 37.2 minutes. And we can get the D value. So the D value is here. Right? 21. Good. D value is 0.9. And now we need to know if we added or subtracted. So if we start here and we go down to the next one, it's getting smaller. We subtract. So minus 0.9. Minus 0.9. And then we're going to jump into our increments and we'll get the GHA for these increments and the correction for this D value. So 23, here's the minutes, 19, 27, there they are, 23. So now the planet is the sun, 23 minutes and 27 seconds. Here's the seconds, 27. So here's our correction, 551.8. 23, 27, it's 551.8. 551.8. It's 551.8. Good. And now let's get our this D correction. Or this D has a correction. Everything's got a correction. Here's 9. Here's our 0.9. And they want us to use 0.4. So 0.4, and we are subtracting it because it was getting smaller. So we're looking at south 10. Okay, let's just do that on the calculator rather than adding all this borrowing. 37.2 minus 0.4 equals 36.8. 36.8 minutes. This is our declination. South. Okay, now we'll add these GHAs together. 5 and 8. Just do this on the calculator. 34.5. 34.5 plus 51.8 equals 86.3. 86.3. And then this is 226. 226 degrees, 86.3 minutes. Okay. And now we are going to add an east longitude. I'm going to convert this 86. See how it's over 60? I'm just going to subtract 60 from it and add it to over here. So if you subtract 60 from here, you end up getting 26.3. And that 60 goes up here. So 227. 227 degrees, 26.3 minutes. Okay, now we're going to add an east longitude. If it was west longitude, we subtract. But we add east longitude, and our east longitude is up here, 80. It's 80 degrees, 14.0 minutes. I'm going to add these. So 3 plus 0 is 3. 4, that's 10. 1, 3, 4. 40.3 minutes. And 7 plus 0 is 7. That's 10. 307. 40.3. This is the LHA of the sun. Local hour angle. Sun is equal to this. There we are. Now we have the pieces we need to work with the site reduction tables and tabulate these. So we are saying declination equals, and then we got our DR lat. Let's make that a little better. DR lat and our LHA. These are what we need. So our declination is south 10. South 10 36.8. 36.8. And our DR lat is here. 2144. 21 degrees 44.0 south. And our LHA is 307. 307 degrees 40.3. 40.3 minutes. Okay. Now we need to say declination and DR latitude are the same. They're both south. So we can say dec and DR lat are same. That is important. And now we need the base argument. They call it an argument. Base argument. And that is the degrees. 10, 21, 307. Base argument. 10, 21, 307. Okay, and now we get the base angle, or Z, the base Z, and we get this from the site reduction tables. All right, and we're tabulating. Okay, so what are we looking for? We need the LHA of 307. LHA 307. So if we find 307, interesting thing about this book, it's kind of split into two. So 307, right? In a latitude of 21. But the 21's not on here. We're saying 307, but there's no 21. So there's another half of this book. So we need to find 307 in the other half of this book. So you'll see it goes up and up, but if you keep going, it jumps back. So it's going, see, now it's back in the 200s. We need to flip to 307. There, 307 LHA, and now we are same. So we're same 307 21 10. 10. Good. So we're same 307 21 10, and here's the Z column, 93.7. Our base argument is 93.7. Okay. 93.7. 93.7. 93.7 and 93.7. Okay, so now we need to get our tabulated Z. This is the fun part. Tabulated Z. So to tabulate Z, what we're going to do is take our base argument, knock this one up by 1, so it's 11, 21, 307. And then to tabulate this one, it's 10, 22, 307. And then to tabulate this one, it's 10, 21, 308. So let's do all these steps. It's all in the site reduction tables. So now we're looking at 11. So we simply just move this DR, this deck, down 1. Make sure we're straight. So now we're same 308, 21, 11. And we are here, 92.5. 92.5. 92.5. And now we scoot this one up, so we're looking at 22. So we make sure this is at 10. 22 is over here. So we're same 307, 22, 10. 94.4. See declinations on this side too, so you can see we're 10. 94.4. 94.4. And now we need to move this 307 to 308. So that one's a little bit, here we go. So now we're back to 10. And now we are same 308, 21, 10, 94.1. Good. 94.1. It's worth taking your time and double checking. 94.1. Okay, so now we figure out the difference between these, the difference in Z, which this is less than this one, so it's going to be subtracted. This one's more. I like to figure out the signs before I start doing the math so I can keep everything straight. But if you type this number into your calculator first and subtract this, you'll get the right sign. So 92.5 minus 93.7. Ha, my calculator's not on. That's funny. 92.5 minus 93.7 equals minus 1.2. Do this one. 94.4 minus 93.7 equals 0.7. 0.7. One last one. 94.1 minus 93.7 equals 0.4. And now we can find the correction. And the correction is equal to, now let's back up the increments. We need to put the increments up here so we can find the correction. The increments are equal to the minutes here. So 36.8, 36.8, and 44.0, and 40.3. Here's the increments. Now we can find the correction. So the correction is equal to the difference times the increments divided by 60. Let's see what that looks like. So, negative 1.2. Negative 1.2 times 36.8 equals divided by 60 equals minus 0.74. Minus 0.74. Now we come down here, 0.7. 0.7 times 44 equals divided by 60 equals, that's can't be right. So 0.7 times 44 equals divided by 60 equals, 0.5. I always try to do a little bit of mental math and make sure I'm at least close. So 0.4 times 40, 0.4 times 40 equals divided by 60. Well, 0.4 times 40.3 equals divided by 60 equals 0.27. 0.27. And now let's find the total correction, which is going to equal, so you got negative 0.74, negative 0.74, plus 0.5, plus 0.27 equals, wow, very small correction. It's essentially 0. It rounds to 0. We're just going to make it 0. So total correction is 0. Total correction of 0. So let's come over here and keep going here. So we're going to take our base, Z. Base Z is equal to 93.7. 93.7. Our correction is 0. That makes things easy, which means our Z value comes out in quadrantal notation, and it's 93.7. We need to name this thing. Is it north or south? We name it same as drlat. It's south. And then we need to name it east or west. So if LHA is greater than 180, it gets an east. Good. So east. So now we need to figure out Zn. And we can do that by, let's lay this out in a graph so we can see this. So we get north, south, east, and west. And now we're starting south. So we're south. And now we're going east. And we're 93. We're over 90. So we're just out here. So here is our Z. And now we need to say Zn is this, right? This is going to equal Zn. So how do we figure this out? This is 180 minus Z will get us our Zn. So we're going to say 180 minus Z is equal to Zn. So 180 minus 93.7 equals 86.3. Zn is equal to 86.3 degrees. And now let's correct our compass. TBMDC. If we're going down, we add west. So true variation magnetic deviation compass. Our true, we just calculated 086.3 degrees true. And our variation is given 5 west. We go down, we're adding west. So we get 86.3 plus 5 equals 91.3. 91.3. We were given the sun bearing of 96.0 degrees PSC, and we're adding it, right? From 91 to 96, we're going to add. So let's see. So it's west. So 91.3 minus 96 equals 4.7. 4.7 west is our answer. Let's see. Ha! Look at that. 4.7. We nailed it. So that is the answer to practice problem 5, determination of compass error by azimuth of the sun.